Okay, section 15.7 is about triple integrals and cylindrical coordinates. In this video, I'm just going to focus on introducing cylindrical coordinates. Cylindrical coordinates are just r, theta, z. So it's essentially just we're using polar coordinates to describe the x and y coordinates of our point, and we're still going to have z is equal to z. So the connection between this and rectangular coordinates is exactly what we're used to. If this was the xy plane, I'm just going to plot a point in quadrant 1, which is kind of the nicest point. And this triangle here gives me a nice picture. That side is x and y. There's my r, and there's my theta. Okay. Now, let's remember that in polar coordinates, and this will extend to cylindrical coordinates, points like this have multiple names. This, I think, would be the simplest name I could choose for this point, where r is positive, and I chose theta to be the smallest positive angle I could that goes from the positive x-axis to the ray that would pass through that point. Okay. But another name for this point, I could have theta rotate all the way around, and then a little bit more. I could have a negative theta that rotated around this way. If I really wanted to, I could have r be negative and have theta be an angle that pointed into quadrant 3, so that r being negative would flip me back into the opposite quadrant. In theory, that's all possible. We're only really going to be using cylindrical coordinates for integration. Okay, so for integration, we're going to restrict r to be bigger than or equal to 0. Okay. Some textbooks actually restrict r to be bigger than or equal to 0 all the time in cylindrical coordinates. Our book does not, but for the purposes of integration, we're going to need that. Okay. All right. Now, this triangle basically tells me how to convert back and forth between rectangular and polar coordinates. I can see from this triangle that cosine of theta would just be x over r. Well, if I solve that for x, x is equal to r cosine theta. You probably already have that accidentally memorized. If not, accidentally memorize it. Accidental memorization, don't create flashcards and just try to memorize it. Draw the picture, derive it a gazillion times, you'll know it. Okay. Now, this picture supposes that theta is acute and r is positive and x and y are positive. Turns out that this picture can help me remember a formula that works all the time. So even if I were in a different quadrant, using a different value of theta, this would always work. Okay. Similarly, sine of theta is equal to y over r, which means that y is equal to r sine theta. And that always works. Okay. So, this is how I can express x and y in terms of polar coordinates, which then allows me to express x, y, z in terms of cylindrical coordinates. X becomes r cosine theta, y becomes r sine theta, z just stays as z. Okay. All right, of course, going the other way, I've got that x squared plus y squared equals r squared. That's going to imply that r is one of two things, either the positive or negative square root of x squared plus y squared. If I'm just using cylindrical coordinates to describe a point, I could choose either one as long as I chose a theta value that was consistent with that. So again, if I wanted to describe this point using a positive r, my theta would have to terminate in quadrant 1. If I wanted to use a negative r, I'd have to use an angle that put me into quadrant 3, so that when r is negative, that flips me back into quadrant 1. Now, for our purposes for integration, r will have to be positive, so r will be the positive square root of x squared plus y squared. Okay. All right, and then if I look at theta, tangent of theta is going to equal y over x. Okay. Now, that's not enough information by itself for me to solve for theta. I can't just take inverse tangent of theta, because that would give me always an angle between negative pi over 2 and positive pi over 2, and theta doesn't have those restrictions. So let's just practice converting a point from rectangular coordinates to polar coordinates, we'll go from rectangular coordinates in 3 space to cylindrical coordinates in 3 space, just to review how that works. So let's say that I had x, y, z is equal to 1, negative 1, 2. And I want to find our theta z. 2 is 2. Z doesn't change. Z means exactly the same thing in cylindrical coordinates as it does in rectangular coordinates. What I have to do now is just figure out my r and my theta. To do that, I'm going to plot this point in the xy plane. I've dealt with the z, so I'm just going to plot 1, negative 1 would be here. That gives me this nice triangle. This side length is 1, this side length is 1. I've labeled the actual side lengths. I know this point is 1, negative 1. I can then solve for the radius r. That's just going to be the square root of 2. I'm choosing to make that positive. By choosing to make r positive, I'm committing to my theta being an angle that will land me in quadrant 4. What I know is that tangent of theta is going to have to equal y over x, so that would be negative 1 over 1, which is negative 1. Now, in this case, if I wanted to, I could actually use arctangent, because arctangent gives me an angle between negative pi over 2 and positive pi over 2. And so I could say that theta is equal to negative pi over 4. That is an angle whose tangent is negative 1. That is in quadrant 4. I think that's probably the simplest choice, but if I wanted to have a positive value of theta, I certainly could. If I wanted to make that my theta instead, I would simply say, hey, that reference angle is pi over 4, so I could also have let theta equal 7 pi over 4. But it does have to be an angle that's going to be in quadrant 4, so I really need to plot the point so that, because tangent of theta equals negative 1 has infinitely many solutions. Only half of those infinitely many solutions are in quadrant 4, the other half are in quadrant 2, and I can't have an angle in quadrant 2 with a positive radius if I want to hit that point. Okay, so that's just a quick review of converting points. I want to also take a look at some equations for surfaces. I want to start by taking a look at what a constant surface looks like. Because I know in rectangular coordinates, if x is constant, that's just a plane parallel to the yz plane. If y is constant, that's a plane parallel to the xz plane. I want to see what happens if r is constant. Let's say r is equal to 5. Okay. Well, okay, I'm going to first of all draw that in 2 space, in the xy plane, and then I'll draw that in 3 space. Okay. So, viewing this as just a polar equation, r equals 5 would just be a circle of radius 5. Now, in cylindrical coordinates, this equation doesn't put any restrictions on what z can be. So what I'm going to get is the vertical extrusion, the vertical extrusion of that circle, I actually get a cylinder. So in cylindrical coordinates, if r is constant, I'm going to be getting a cylinder. Okay. Now, if z is constant, I'm going to return to theta and do that last. If z is constant, let's say we had something like z equals 2, well, that's the same as it would be in rectangular coordinates. That's just going to be a plane that's parallel to the yz plane. And of course, the way I represent a plane is with a parallelogram. So this is just going to be a plane. Now, let's take a look at if theta is constant. Let's just suppose theta is equal to pi over 4. And I'm actually going to do this one twice. I'm going to first of all do it with no restrictions on r. And And then I'm going to do theta equals pi over 4, where r is bigger than or equal to 0. Because most of the time, we're going to be using cylindrical coordinates for the purposes of integration. And just like when we integrate in polar coordinates, we're going to require our r values to be non-negative. Okay, so I'm going to start by drawing just in the xy plane what theta equals pi over 4 would look like, viewing that as a polar curve, and then I'll draw it in 3 space. So if theta equals pi over 4, that's actually just this line where this angle is equal to pi over 4. Because I've got to rotate pi over 4, but then there are no restrictions on r. R is free to be whatever I want, including negative values. So negative values of r would give me this half of the line. Positive values of r would give me this half of the line. Okay. So if I go to graph that in 3 space, pi over 4 in the xy plane would look something like that. And then I'm just doing the vertical extrusion of that. So I would be getting a plane. Now, if I restrict it so that r is positive, then instead of getting a line in the xy plane, I would get just a ray. And then, when I go to graph that in 3 space, I would just be extruding that ray. So I'm going to get a half plane. So, if r is constant, I've got a cylinder. If z is constant, I've got a plane. If theta is constant, and I'm just in cylindrical coordinates, no restrictions on r, I get a plane. If theta is constant but r is non-negative, I'm going to be getting a half plane. Those are the constant surfaces that I can get in cylindrical coordinates. Okay. Next video, we'll take a look at some other sorts of surfaces that we can get and how we describe those in cylindrical coordinates, and then we'll start doing some integration.